All right, we're back and we're looking at the notes from the last couple of weeks, which Eric took.
So we start by reviewing them, yes. So over the past couple of weeks, we mainly talked about what we could do at the intersection of machine learning and robotics, okay. Especially because of the things moving over the past few months, things moving well on machine learning, especially around the LLM and so on. So we reviewed 2 weeks ago. We reviewed several links we have stashed into several of our threads on the Discord server, okay. And we discussed especially some recent approaches. What was interesting 2 weeks ago is that we discussed about what is called the universal controller problem. Okay. So the idea is to have one piece of software that you can run on many robots, okay, and this software would be able to control them regardless of the actual hardware. Okay. And so that's still, as far as I know, and as far as we found out 2 weeks ago, that's still an open problem. However, there are different approaches depending on the era we are. So, are we talking about optimal control, okay, adaptive control, such kind of things, more linked to cybernetics, which was more popular a few decades ago, okay? And now the approach is based on machine learning and more recently large models, basically. So we've discussed a few of these things 2 weeks ago. So the detail is written in the detail. So some of the detail is on the document on Rome. Okay. And last week we covered quite a few topics. So we discussed about the hardware, about we talked about having an MCU and a CPU, okay, inside our custom build. Okay. But last week we extended the idea to have more compute, actually, okay, of different kinds. Okay. And the reason for that is because there is more and more specialized hardware, especially built-in compute directly with sensors. So typically, the one we discussed are the Hawk-D, okay, the depth camera from Luxonis, as well as what we've seen with Intel, such kind of cameras. Okay, so there is specialized hardware that we could leverage, of course. And also, we spent some time experimenting with the ChatGPT. Okay, about. I don't remember exactly what we've done last week.
We were using natural language commands to see if given fake sensor data input, whether ChatGPT can basically do meaningful things. So we gave it things like fake motor voltages and asked it to narrate what it was doing. So I think we got there after initially talking about closed loop action. Then we decided just narrating what's going on is a simpler challenge to start with. So giving it the feed of all the sensors, can it actually tell the story? And it did pretty well. I was impressed that even +3, -3 as the motor voltages, it actually detected and said this is turning or pivoting in place, and it detected conditions like turning and so forth. So it can basically do high level, low precision, low accuracy, kind of sensor fusion and interpretation. That was my takeaway, right?
Yes, that's pretty cool. And but something very interesting is that it's with natural language, it could be a component at the intersection of all the compute. Okay? That is some of the compute. So, for example, the compute on a sensor, okay, is specialized and deals with the sensor data, basically. Okay, and still ChatGPT can ingest such kind of data. Okay, and as Venkat just explained, narrate it, explain it. Interpret it, okay. So adapt this raw data to basically to some other format for other compute to use, okay, as well as external users like us, okay, to understand what's happening. Okay. So
It will
sorry,
be
Dr.
interesting to try this with this what 1 million context like Gemini Pro, because that seems to have some emergent properties when you have this long context length of tokens. So yeah, that would be interesting to see what can be if lots of sensor data is like fed into uh, Gemini Pro, what we get.
Yeah. So definitely there is more. There are more experiments to conduct on that. What was very interesting is to have just a raw numbers and to attach to some of these numbers some meaning, okay, and to ask ChatGPT to extend explanations based on these small seeds, basically on raw data, and indeed that. It didn't take so many trials, right, to get really interesting data last week. Huh?
We did it live.
Yeah.
I'd like to make two comments, Eric, about what you just said. We have two different goals in mind. One of them is, can we use an LLM or LVM as a logic processor, narrative logic processor for a rover? That was one question. So step one, is it able to take data and turn it into a narrative? But a different issue is, one of the things we're trying to do is make rovers more accessible to hobbyists. And the question we asked, could LLMs be used to make it even more no code? And one of the requirements that you have is you have to have a way for the user to get information about what's happening inside the rover. And this appears to be a very, I can't say natural, a very non-programmable way of understanding what's happening with your rover. Okay, so we have these two different goals, and the answer for both of them is it's not unreasonable to do it.
Yes.
So when all is done, we would like to have a no-code rover brain that is not only good but also accessible.
You are muted, Venkat.
Sorry. Yeah, so I just wanted to like highlight a couple of things we were discussing last week, which I think are still open technical discussions we should have. I think one is, what is the configuration of onboard processing capabilities that makes most sense? So that would be, we already talked about small brain, big brain, so MCU plus RPi. And then if you add something like a Jetson Nano and an OAK-D, which is kind of like throw everything at the onboard kind of situation, what's the configuration of those things? And we talked about, like, is it a 4-layer stack where you have like application specific ML like the OAK-D at the uppermost level of abstraction, below that general machine learning like Jetson, below that general compute like RPi, and then MCU? Or should we think, for example, like the Nano and the RPi can be like right brain and left brain for different types of tasks? And we talked a little bit about, can we like usefully segment tasks in a way that mimics the human brain, like, right brain thinking, left brain thinking. So we had that discussion. Then we decided to try this chat GPT thing. And I think this brings up another question, which is, if it is connected to online large foundation models, that's fifth layer of the stack. It's like what it can do locally on board versus what it has to outsource to ChatGPT. So this narration logic loop, I don't know if it can actually be done with onboard available processing power. So if we had like Llama file running on either RPi or I don't know if it runs on Jetson. If we had it on some onboard hardware, could you run this narrate and act kind of loop on board without an internet connection? So those are the two open questions in my mind. Overall architecture and load distribution between onboard and remote computation.
You don't need the ARPA if you're using Jetson, right? It has a CPU.
Okay, so
Yeah, so it's like a ARM Cortex plus GPU.
it's kind of like a useful. Would be nice to have a useful table of comparison. Maybe actually ChatGPT can do that.
Yeah.
Let's see. Yeah. We'll stop sharing and let's see if I can.
Or we could use a Raspberry Pi with an accelerator. We could connect because the latest Raspberry Pis have a PCI 5 Express connector, so we could just make a buy an accelerator that connects to the PCI Express connector and then use that accelerator. There are two ways to go.
All right, let me share. It is producing something. Yes. So I asked compare the RPi 4 and they've released the RPi 5, right? And there's also the what is the machine learning one, the new one. I forget. But okay, yeah, this is the comparison. I'll scroll up slowly. Ask me to stop, and actually maybe this is above my pay grade to properly narrate the differences and what their significance is. For example, I see this is.
Well, you didn't ask ChatGPT to tell you what the significance is.
I will in a second after we look at the raw comparison.
It looks like the processor, the general processor, is weaker on the Jetson.
Can you scroll up a bit?
Hold on, let me ask it another. While it's generating that, all right, what did you want to look at?
Yeah, so the RPi 4 has a A72, so that came out later, so it's a more powerful CPU than the A57.
Okay. Slightly
but
strong.
it doesn't have the GPU.
I consider the CPU of the Jetson to be used for managing the Jetson, not for robotic activity, even though I know it can be used for both.
So that's actually a load question, right? Given if you're trying to run something like Llama file, will you end up using all of the CPU just to manage the running of that, or will there be spare capacity left to do like CPU-ish tasks?
Well, we saw that at least on a regular desktop computer, Llama doesn't use too much CPU.
All right. So here are some similarities and differences.
But it uses a lot of memory, or could use. It uses 200, 300, 400 megabytes.
These are very generic sounding similarities. Let's look at differences.
But if we want a more powerful CPU on the Jetson, there is, I think, a new version that came out last year called Jetson Orin.
Oh, okay.
That might have a powerful CPU plus GPU, but that will be more cost.
And it'll be heavier power, right? The Jetson Nano is meant for small robotics, and the regular Jetson is for like.
No, I think it can run up to. So I think it has like 5 watt, 10 watt, 15 watt power level selections. So we can run it at 5 watts. We can ask what's the difference between Jetson Nano and Jetson Orin.
It would be nice to have ChatGPT as an audio participant in our Zoom meetings, so we can just ask orally, can you say something, right?
Whenever I have voice controlled ChatGPT, whenever you press the space bar, whatever you say goes into the prompt. So
But
we
still
can
doesn't
try it.
narrate it, right? It's not participating as a like live player like us.
Why not? I decide when a prompt ends. Okay, the minute I let go of the space bar, it receives a prompt and it carries it out.
Oh, oh. So this it is more power hungry. It doesn't tell you how much, but this nano goes as low as 5 watts. I assume Orin will be like closer to 20 watts in normal configuration. I think we at some point we were looking at something and it said about 20 watts. So okay, so I think the broad point you made, Anuraj, is kind of roughly correct, which is we shouldn't think of like Jetson plus RPi as like right brain, left brain. It's more like Jetson is whole brain and RPi is left brain, something like that, right?
Well, RPi can be made whole brain. You just have to add an because the new Raspberry Pi 5 has a PCI Express, so you can add accelerators quite easily there.
All right, let's compare RPi 4 and RPi 5.
You
What
can
was
tell it
the
for robotic
one?
application.
Let's compare the third one too. What was the name of the AI RPi? Turing Pi, right? Is it Turing Pi
Turing Pi.
or something? There's a new one.
Turing Pi is a cluster
Tell him.
technology.
Okay, so there is no AI specific one. All right.
After, for the Raspberry Pi, and anything with a USB port, we can have a Coral or a Coral TPU, or there was the Intel one, the I forgot the name, the NPU.
No, you don't need a. Well, basically, the Coral accelerator is available as a M.2 connector, and that we can connect directly with a hat and the PCI Express. So it will be much faster. With USB, it
Can't
will be
you
a
tell
little
him
slower.
Can't you tell him to search the internet for information about Raspberry Pi 5?
Okay.
Are you doing plain ChatGPT or ChatGPT with?
I just decide by context what to do, so I'm not using a search for. Should switch to searching with Bing or whatever. Oh yeah. So it is okay. So I'll save this chat and put it somewhere in a room or something. Okay, so these are our options. So for Yakasar, it sounds like the two options now are the latest version of the Jetson, the Orin running at the lowest power, or an RPi 5 with what was that accelerator you mentioned, Anuraj? Orin? No, Corel?
No, we can use like there is like the Google's Coral TPUs, and so we can use anything that can be accessed via this PCI Express.
But there's going to be like power and form factor limitations on what you can actually attach to an RPi 5 onboard rover, right? Like PCI Express slots are quite physically wide.
No, so
No?
if you open the open the page of Raspberry Pi. So it is a small. So PCI Express small as like a small port. It's like it doesn't have all the pins. So if you see on the left hand side of the figure, there is a on the Raspberry Pi diagram on the board itself. If you
Let's,
see
is it in documentation?
in that figure itself, if you see there is a white colored Raspberry Pi, right?
Yes.
Yes, white color Raspberry Pi logo.
Yeah, I see that over here. Okay.
That logo on
Oh,
the
yeah,
left hand side, it's that is the PCI Express port.
okay, and what will plug in here is kind of like a feather-sized port or something, or it'll go with a. it won't be a cable,
Well,
right? They're on
no,
direct.
it's like the flex cable that goes into the cameras. Have you
Okay.
seen the cameras that? So it
Yeah.
will be something like that, and then what people do is like have a hat, and then that hat has this the other end, and then they have this M.2 connector on it, and then you can just slide in the M.2 accelerators there. So some people attach FPGAs, people attach different sort of like accelerators or corals, anything you can, anything that can be converted from M.2 to this PCI Express can go on Raspberry Pi.
USB, this Coral AI, is this what you're talking about?
Yeah, but there is a M.2 version of it.
Oops.
I think, yeah. So if you see,
What
yeah,
is
so in
that?
the middle, yeah.
This
So
USB.
How big
M.2.
is it?
So if you see the
How,
top or top images, so you see in the middle, yeah, those are like M.2 connectors.
This
That is
thing.
M.7, but on the right hand side, yes,
Anuraj,
that
how
one.
big is this device?
It's it will fit on a Raspberry Pi
Yeah,
on the
this.
top of it.
Oh, on top of it.
Yeah,
Yeah,
this looks smaller. This second one from the left looks like a RPi-sized board, which means all
yeah.
these are like the feather board size form factor. Okay, so this makes sense. So to summarize, if I understand correctly, you have an RPi-5, then PCI Express, you connect it to a hat, and then the hat has an M.2 connector in which you plug in this Coral
Yeah,
board. Is that the configuration? Okay.
yeah. So it doesn't have to be a Coral board. It can be an FPGA or any other form of specific accelerator.
Okay. And this would create something that's approximately equivalent in power to Jetson, like apples
I
to
think
apples
it
type
might
way.
be a little lower.
Okay.
Yeah, depends on. Yeah, it might be the same because Jetson Orin Nano would be the same as this one. And
Okay. Let's see. Hmm, share this tab again. So I think
Also, you have many ersatz of the Raspberry Pi. Okay, I'm thinking especially about the Orange Pi, which have an M2 connector, M.2 connector right on the board, so there is not even need for any hat. So it can be even smaller, similar form factor for the main board, okay, but the whole thing can be even smaller, I believe.
so this is another accelerator. It's called Accelera, and they make specific like computes for accelerating compute. And yeah, it's available as a. It's in the private chat. It's available as a M.2 connector, and then you can plug it somewhere. Yeah, I met these guys at the RISC-V conference last year.
But what can it do? In other words, how long will it take the M2 to program, to fine tune Llama?
Well, I don't know the specs, but yeah,
No,
it's
I
just
understand, but that's like a benchmark.
it has like a 512 MB DDR, so it might be comparable to whatever 512 MB GPU, NVIDIA GPU. So this seems like specifically like dedicated to edge. So I think the Jetsons come in 2 GB, 4 GB, 8 GBs. This is even smaller. So this power consumption of this accelerator might be less than Jetson. I don't know like how it's programmed. I didn't check that. It has some SDK. If you go to the all AI product solutions, so they provide their own stack.
Right.
Yeah,
What's
and then
interesting that
Voyager.
there are more and more specialized hardware like that. When I say specialized, it's for embedded or stuff like that as well. So they have different capabilities, different performance, and different trade-off with power, basically. Okay? Because some of them, a few years back, a lot of them were about CNN, convolutional neural networks. Okay, and so the architecture was really specialized to for each watt spent on computer to make the most in terms of CNN. But now it's the core is not the CNN anymore; it's the transformer architecture, and there are several new architectures that try to get the most they can do with the watts for transformer architectures. So basically, it depends on the application, the underlying application. CNN was very popular for object recognition and so on. I think it's on some benchmark. I guess it's still the most powerful. I'm not even sure actually. But now there are more language models that are that they try to really optimize on these specialized hardware.
Yeah, this is, I think, kind of like these arms race going on now. Looks like all accelerator companies are both they're trying to hedge their bets against this kind of model zoo approach of running as many variety models as possible at the client level, plus kind of bet on what happens if the transformer cell models are able to do everything much better, which kind of like leads you down different hardware evolution paths a little bit, I think. But this is actually a good diagram to pay a little attention to, because I've seen a few diagrams and they all look vaguely similar, where they give you like some runtime, some low-level stuff, some sort of like interfaces to PyTorch. Here you have a TVM compiler. The company I consult for, TensorTorrent, has a very similar architecture. And yeah, and at the top, they usually have like out-of-the-box ability to run a bunch of models, and then you have your own models that you run, which can either be refinements of the models they've already supported, or you kind of like run them from scratch. But
Yeah,
yeah,
problem is like we have to learn all these.
yeah.
For different accelerator, you have to learn a different SDK. That takes
So
time.
I think this means there's like two important constraints in the bounding box. One is on the hardware side, the power budget and how much we can afford to run. So if it's like 20-watt overall onboard power, how much ML can you actually run? And the other constraint is how complex is the software stack? Is it something like you download in a llama file binary and then it becomes like a natural language, low code, no code kind of like top level thing, or do you have to like do messy stuff with PyTorch to get anything to run at all?
Don't forget, you can have the AI tell you what to do with PyTorch. Okay, it can help you do the fidgety stuff.
Yeah, but not in. I'm making a distinction between like runtime while the rover is up and running, what's running, and how much of that code is like out of the box, low code, no code, versus stuff we have to write with or without AI assistance to do stuff. Does that make sense? Like even with AI assistance, if we have to like actually write new code to I don't know, make the stack usable for our application, that's like a huge bottleneck.
No, I agree. It's like installing hardware in the old computers. Opening the computer and putting in a board is beyond what anybody wants to do. But even if all you have to do is crawl under the table and plug something in and back, it is still more than a lot of people are willing to do.
Yeah.
While clicking on an internet website to download software which self-installs in your browser, that's much easier.
So this is, I think, a good fork discussion to have a full session on later. But I think we've run into this several times of like hardware and software constraints. Once you like make reasonable decisions on hardware, the driving constraint is always the software. Like we've had 3 versions of that, right? Like the BeagleBone and RPi are very similar boards, but the BeagleBone has been very messy and difficult to get anything with. I thought it was just me. Rhett has not been able to do anything much either. So that's one example. The other is, what was the thing, Anurag, you brought up that we discussed for a while, why am I blanking on this? The RTOS versus the one from the other guys.
You mean Zephyr?
Yeah, Zephyr. Yeah, the Zephyr discussion was very similar. It's like one is much harder than the other, but maybe it supports different hardware. And I think we're now at a third thing, which is the Jetson Nano is one stack, and the RPi plus Coral is another stack. RPi plus this Accelera or whatever is a third stack. So we kind of have to like do a comparison and see which one is the sort of like most robust and easiest to build on, and the two may not be, they may be in conflict. Like the one that's robust and long-term, the best thing to bet on may not be the easiest to program on now. All right. What's next? I think we've reached a couple of like soft decision points for anything we actually choose to do in the future. But yeah.
So before we change topic, just one question. Do you know, Anuraj, whether this Accelera hardware is available easily, and about the costs? So I didn't check the...
I don't know.
Because that's one problem with the TP. Yeah.
I think it's already available. It's like $150.
Yeah, I think I saw that number somewhere. All these things seem to be in that price range. Low-level edge AI accelerators are in the $150 range. Yeah, 149 euros a year.
Okay.
And let's see, let's compare Coral as well.
Like, yeah, it's also a decision on the software stack we'll use, right? Because like if we can go one way, then it's like we have to learn that specific software stack.
This USB
seems to be
accelerator
cheaper.
Sorry, yeah.
Seems a little cheaper.
Yeah, this is $17. This is the one I think you were pointing at as the M2 connector board, right?
No, these ones are integrated already, yes.
Yeah, but it's between, cheapest one is $59, but it's all in this range, $129, $99, $79. So
yeah, here you have the mini PCI accelerator, $24.99. Okay.
So this, I can't imagine it'll do a lot if it's this cheap. So there's a $25, slightly longer one. But if we can get anything interesting done with this level of cost, it'll be very interesting. Oh,
what is the SDK for this?
This one says TensorFlow Lite for this one, M2 accelerator with dual edge. Oh yeah, all of them are TensorFlow Lite. TensorFlow, though, I think is kind of obsolete. Like even Google itself, I think they, what is that, JAX or something is what they prefer now.
There are different approaches, right? Isn't JAX, I don't know.
I think TensorFlow Lite is still the one that will be used for edge devices, and then JAX is something that they use for the HPC compute.
Okay.
Which one does NVIDIA use?
NVIDIA has its own stuff.
Right.
NVIDIA uses CUDA.
But CUDA is a lower abstraction level thing. So TensorFlow, PyTorch, JAX sit one level of abstraction above CUDA. So NVIDIA basically gives you bare metal plus the bottom two layers, and then you can put TensorFlow or PyTorch or whatever on NVIDIA hardware. But Jetson in particular, I don't know what it supports. Let's look at that. see, Jetson Nano Developer Kit. Okay, it uses the NVIDIA Jetpack SDA used across the entire Jetson family of products. So I guess the comparison is now Jetpack versus TensorFlow Lite versus whatever the hell the Accelera was using, which was its Voyager SDK. And I think those are the three. Yeah. So we should make a note of that in the notes page. So frameworks are Jetpack for Jetson, then TensorFlow Lite, and Voyager. All right, so I made a note in our notes page. So this should be a full session where we look at these and compare. But am I missing anything? Is there any other software framework we might end up using that we should kind of be aware of at least?
Yeah, but these are all low level. Would we be using TensorFlow? The level we're talking about?
I think it'll constrain the higher levels. That block diagrammy thing that let me go back to, oh yeah, the block diagrammy thing. This is running on top of something called the Metis runtime. I think that's the level that maps to like TensorFlow or PyTorch. Or no, wait, it's a couple of levels higher. TVM compiler, PyTorch. So this block diagram basically is built around PyTorch. So I think it would constrain but not determine. There may be other pieces on it, but you'll make a basic bet on PyTorch versus TensorFlow ecosystem versus some bespoke thing. And then beyond that, there'll be other stack pieces to think about. That's my sense. Let's look at Jetpack better.
Jetpack is basically everything. The OS plus whatever CUDA is coming. It's like a package.
Okay.
It's the Linux package for Jetsons.
But the AI piece you think is just sort of like cut down version of CUDA with some extra stuff?
Probably.
Okay. So let's bookmark this as a worthwhile full-hour discussion. I think it'll be interesting to compare these frameworks.
Yeah, but like we also have to check like how much of these will be surviving in a couple of years and what will be, because it keeps on changing, right? Maybe CUDA will still be there. TensorFlow's popularity is going down.
Yep. But I think it's worth at least. Remember when we were doing the Yakasor architecture, we spent like 2 weeks evaluating a couple of different options, and then I don't know what we ended up doing. But yeah, we can do something similar here. Like have a couple of basically deep dive study sessions into these things, and then kind of decide if there's going to be AI, how we are going to like put it on the Yakasor. But yeah, Jetpack is CUDA at the low level, and then there's like this thing I think is the equivalent of like TensorFlow or something, TensorRT. It's a deep learning inference runtime, so it's not quite. Multimedia API, computer vision, graphics. Yeah, okay, this was supported SDKs and tools. Okay, yeah. Triton, I think, is from OpenAI. It's kind of like a simplified way of doing CUDA programming. Isaac is the one I think they use on the bigger things. Yeah, I'll stop sharing this. Okay. Okay, so I think this kind of wraps up. Let me capture the decision points. Let's see, where are we?
I think the answer to which framework is the one that gives us flexibility in the frameworks that we actually use. Because we do want low code.
So I've separated those two decisions because I think there's almost a matrix of like, if it's a TensorFlow based architecture, what sort of like full
Yeah.
stack low code is available on that particular option, right? And hardware configs are basically Jetson Orin, I think, is the one we should think about, versus Coral, and the third one, Accelera. And if you find or hear of something else in the meantime, before we get around to discussing these, add it to this list. So when we do our full comparison session, we can work on this. Anything else I should capture here?
You could just add FPGA directly.
So that should be in.
Yeah.
How hard is doing things directly in FPGA? I've heard it's a very black magic type of work.
There are HTLs coming in like Python-like languages. So I think if you search for Amaranth lang,
How
so
do you
it's like
spell
a
that?
Python-like, yeah, Amaranth, Amaranth.
It's a language.
Yes, it's like Pythony alike, and then it generates HTL, and then I think it generates RTL.
Okay. Yeah, but this is. I would say this is a couple of degrees removed from anything I would attempt on my own. But if somebody wants to try this, it'll be.
Yeah, so
Well, actually,
basically, I think it's like it sits on top of system Verilog, and then it just generates probably system Verilog or VHDL, and then that gets converted to some sort of RTL.
okay, but once you like, how do you get there? Like, suppose I decide I want a rover with this AI capability of like running a local language narrative action model, and I have like some high level llama file type thing. I'm missing a few steps. How do you get from
No, yeah, basically this is for like specific compute acceleration. So if you know the compute, what sort of let's say if you have a specific set of matrix multiplications, and then
okay,
you want to accelerate those specific compute. So with that, this you can basically write some VHDL or Amaranth, and then
okay.
generate the RTL for that.
So then this would be low-level kernel APIs exposed to something like PyTorch, or actually below the PyTorch to the graph compiler level, where the graph compiler is available, that this it knows that this FPGA is available, something like that, right?
Yeah.
Okay, so that's definitely not something I would attempt. But have you done things like that? I'm curious.
Well, yeah, I've done basic. So I have a FPGA board, so I've been learning here and there, but I'm not a hardware expert. So I can deal with it if needed.
Okay, while we're talking about that, since you've already been also exploring RISC-V, I feel like RISC-V should be in this comparison set we've been talking about.
I think the Orange Pi isn't it RISC-V based?
No. It's not. It's very similar. It's Cortex something. The Orange Pi 5 is pretty powerful though. Huh? It's one of the. It's a recent ARM octa-core something. They
So
may
it's
have
based on the ROC chip, right?
yes. There is one thing that I'm not sure TensorFlow really qualify for low-level framework. Okay.
Does the Orange Pi have drivers for motors?
The Orange Pi?
Yeah.
It's very similar to Raspberry Pi. So basically, any driver that would compile on the Raspberry Pi is likely to compile.
No. I mean, when I said driver, I meant motor power supplies.
It doesn't look like it. I think this is
I meant-
standard 5-volt type compute. It can't run like higher current draw or voltage motors. So it's not a robotics capable hardware, I think.
You can check the BeagleBone's RISC-V board, which has an integrated FPGA on board. What was it
I'm
called?
a little burned on BeagleBone overall, but yeah, sure, we can check it.
It's called Beagle 5 Fire.
All this stuff looks exciting and you feel like buying it and collecting it like toys, but then when you realize what it takes to even get to Hello World or Blinky on each of them, it's like all the motivation drains away. So I want to go to like writing a simple robot, turn the motors on, turn it off level script with the least effort, least amount of configuration, dev environment setup, all that. So I don't know what the right answer for that is. But let's add this to the list of options.
Actually, this is quite a good board. So if you have specific compute, you can do it on the FPGA, and then it has a good ARM processor on the board itself, and then M.2 connector.
I think in terms of deciding which ones of these are like not too fragile to build on, more than like how good the design is. Like the original BeagleBone, I think it's a good design too. It's like how good is the organization and team behind it? Is it like a very poorly funded nonprofit that is always struggling, or is it well funded with lots of big corporate support? I think
So this is
BeagleBone.
aimed. This is not aimed at. So this is like BeagleBone is basically aimed at like industrial. So those who know, those who are working on this on a regular basis will. It's not that difficult to make it run. But if you are a hobbyist starting, then probably a Raspberry Pi is the way to go.
Mhm. But this just
Because this is like, yeah, this is not that easy to get started.
Yeah, this is definitely a very complex thing. Oh, it does have your M2 thing, so you can add your other accelerators to this as well. This is nice, yeah.
Yeah, so the Orange Pi, I was just reading, has only one M2 connector and doesn't have wireless built in. So you have to use up your M2 for the wireless.
Whereas BeagleBone has.
Yeah. So this with that BeagleBone, we could add that Blues wireless on board, and then basically we have like a 4G connection.
Wait, what wireless? Blues wireless? What did you say?
Yeah, the one Yasha suggested for the 4G LTE connections.
How do you spell that?
Blues note card. BLUES note card.
Yes. So there's like core hardware decision points in the picture here, plus for like bottleneck constraints like M2 connectors, which we might need for several purposes. You kind of have to have like a full sense of the overall architecture, where if we are having like 4G and we use it up, that kind of thing. So this is going to be interesting to structure in a more formal way. But these are required for, these use the M2 connector. Is that what you said, Mayor?
Yeah. So
Yeah.
basically, we could add this to the Beagle 5 Fire, and then we have a 4G BeagleBone.
It sounds like this M2E connector is an important constraint to know about. All right. So it's a next generation form factor. So it's like a hard disk type.
Yeah.
Yeah.
PCI Express.
So all these new in the laptops, in the new and the new connectors or RAMs, when you want to add RAMs, they are basically of this form factor, and then you or they are called like the SODIMM connectors, and then you plug this in. It's on like similar to that.
So let me capture this additional stuff. Any other constraints we should capture?
Well, do we care about the size? Size and cooling. I say size and thermal considerations.
Oh, we also need, if you're driving a separate power bus for motors and other higher powered things, you would normally be talking to them through what? I2C or GPIO pins, or like what's the other constraint connector stuff? Is it everything on I2C bus? That's what, 4 pins all around?
It depends on the sensors we are using, but I2C and SPI should be enough. So SPI for the camera, and then I2C for the other sensors.
And there are motor controller breakout boards that will daisy chain on an I2C bus, right?
Yeah.
Okay. Because motor controllers would be what? There'd be Hall effect is 4 lines plus its independent power line, which would be 6 or 12 volts depending on the motor. And it would need, yeah, the edge bridge chip. Okay, so we should. Oh, this is another sort of like constraint decision point. Motor control is breakout boards versus single integrated hat. In general, I'm thinking breakout boards is the more flexible strategy because a robotics type hat, I think, uses up too much, right? It like fits on top and uses up a lot of GPIO.
Well, yeah, it depends on how we want to stack it up mechanically. Because the GPIO, there are like stacks. I think Raspberry Pi has a stackable hat, so you can stack one on top of the other. So if you want to go with that,
And that also means, all right, the hat architecture is another constraint.
because if we have these different breakout boards, then we have to screw it manually somewhere.
But it's more flexible though. I mean,
Yeah.
the hat we have to stack, so it makes a big block. And so if we want something thinner or something like that, the breakout board can be a good alternative.
And if we have multiple things in the compute, they can each individually have that. So if small brain is an Arduino, you can have like an Arduino shield on that and move the motor control to that level instead of running it off the big brain, right? So there's like lots of ways to reconfigure this.
Yeah.
Okay. I think we're beginning to define like the compute architecture problem properly now. But are people generally interested in basically adding AI to the Yakusar architecture? Because so far we've only been talking about small brain, big brain.
No, personally, I think it's necessary, basically, but it could be done later. Okay.
So we should basically design the physical and compute architecture to be expandable to have AI acceleration. But maybe the starting point is just to assume that we have the OGD camera, right? How does the OGD connect to RPi or whatever?
It can
USB.
be USB. Yes.
Oh, USB? Okay.
Yes. But if I'm not mistaken, Luxonis, so the maker, has basically the casing of the OGD leads to USB, basically. But the internals, okay, the board basically inside it, they can customize it. Okay, so they offer the several form factors, a bit like we've seen earlier on the Coral web page, where you have the same TPU in different form factors, basically. Okay. So I don't remember, but 2-3 years back, when they released the first OAK1 and OAK-D cameras, we could get we could buy just the board inside, okay, and we could connect it in different ways.
Well, yeah, it depends on how much acceleration. In the first version, I don't think if we just want to deploy it, why do we need so much of compute there, right?
I think we got started down this whole path simply because there were like so many exciting ML announcements in the last few weeks. We felt like we should be jumping on the bandwagon, at least in a small way. That was, I think, at least my reasoning for suggesting some link viewing parties.
Yes, we had many links to unstack.
Yeah.
Okay, but yeah, starting point is still the same. We figure out how to do small brain plus big brain, and then attach the OGD. And small brain is still basically an Arduino of some sort, and big brain is still RPi 4 or 5, right? Which we should standardize on one of those. But, okay, we're almost at the hour, so maybe we can wrap up by making some notes of what we can talk about next week.
But based on this compute, there are also things that are interesting to explore, but later it's about how these computes interact with each other. Okay, that because some of them are really full computers. Okay, so there could be this built-in redundance inside the YaRG. Okay, the YaRG. So let's say some of the compute has a problem. Okay, then do we have a protocol such that the computer is offloaded to another node inside the architecture?
Okay, that's a good topic to discuss next time. So basically a failover model for using the different pieces of compute in an overlapping way, I guess.
Yes. And so it's about also studying the failure modes and such kind of things, basically systems design, right?
All right. And I guess the next time we have Rhett on board as well, since I think he was the one maintaining a lot of the overall architecture documents, we should kind of like do a full review of all the at least major commitments. Like, what is the compute like? What's the physical structure like? What's the power management like? And then, yeah, we should, late in March or something, we should actually start designing this thing. It kind of fell by the wayside. All right. All right. Any other closing thoughts before I close the stream?
No.
All right.
No, thank you.